Hey everyone, welcome back to week 12 of learning ML through an optimization perspective. So last few weeks we've been building up the theory of convex functions. So we talked about what makes a function convex, first and second order conditions, the gradient inequality, Jensen's inequality, all of that stuff. But today I want to talk about quasi-convex functions, which is a meaningful relaxation of convex functions. And I want to start by connecting it directly with something we already know, because I think that makes the whole thing click much faster. Lastly, sorry about no video last week. I was sick, unfortunately. Here's a result from a few weeks ago. We said that a function is convex if and only if its epigraph is convex set. So let me remind you what the epigraph is. So the epigraph is the set of all points above the graph of f. So epi literally means above. So, convexity, or geometrically, it's a statement about what lives above the function. That region has to be a convex set. So in this case, we have some f, looks like maybe an x squared or so, and the epi is a set of all points that is above f. And I just want to emphasize that the epigraph is a connection between convex function and convex sets. So this is one way we can see convexity geometrically, by looking at the set of the epigraph. But what if instead of looking above the graph, we look at horizontal slices through it? That is, we fix a threshold alpha, and we ask what are all the inputs x where f of x is at most alpha. So consider the following set. We have that S of alpha is a set of x which is in the domain of f such that f of x is less than or equal to alpha. So for example, if we pick alpha to be this level here, then S of alpha in this case would be this line segment, or this region of possible inputs, or x. So this set is called the alpha sublevel set of f. And the key observation is that if f is convex, its epigraph is convex. And that automatically forces every sublevel set to be convex. In other words, convexity implies convex sublevel sets. But the converse is actually not true. You can have a function whose every sublevel set is convex. Every horizontal slice gives you a convex set, but the function itself is not convex. Here's an example to demonstrate how that's possible. Here we can see that f clearly is not convex. One way to see that is if you look at the epigraph, so the set of points above the graph f, clearly the set is not convex because it's not convex. You pick 2 points here and you find the middle point is not in the set, so it's not a convex set. At the same time, you take the alpha sublevel and you take the inputs, and of course it's just a line, so it's convex set. So we see that the sublevel set is convex, but the epigraph is not convex. So we see we have two different geometric ways to see a function, kind of. We have the convexity view, which looks above the graph, this epigraph, and asks whether epigraph is convex. And then we have the quasi-convexity view, which takes horizontal slices and then asks whether every sublevel set is convex. So these are not the same thing. Convexity is strictly stronger, but quasi-convexity is still a very meaningful and useful structure. So that's what we're going to study today. So formally, here's the definition. Some function f from Rn to R is quasi-convex if the domain of f is convex, and for every real alpha, the sublevel set is convex. Now, one of the most useful characterizations of convexity was Jensen's inequality. In other words, the value of f on a convex combination is at most the weighted average of the values at the endpoints. But for quasi-convex functions, we get an analogous inequality here, and I think it's even cleaner to read. Instead, for quasi-convex functions, we have the function evaluated at some middle point is less than or equal to, in this case, the max of the endpoints here. What that's saying is that for a quasi-convex function, the value at any point between x and y cannot exceed the worst of the two endpoints. So it's not the weighted average, just the max. Okay, drawing the diagram here, we see that any two combination must be less than or equal to the max, the endpoint. In this case, f of y is the maximum, so we draw a red line and we claim that the function between these 2 points must be less than f of y. So this is a strictly weaker requirement than convexity. Convexity says you're below the chord. Quasi-convexity says you're below the higher endpoint. You're allowed to dip below both, go down and come back up, as long as you never exceed the worst starting point. And this is in fact equivalent to the sublevel set definition. If every sublevel set is convex, this inequality holds and vice versa. So let's take some examples to make this concrete. So for the first example, let's look at linear fractional functions. We saw this before in the context of perspective functions. So this function is actually quasi-linear, which just means it's both quasi-convex and quasi-concave. To see why, we first take the alpha sublevel, and we get this expression here. Doing some rearranging, we see that this is just the intersection of an open half space and a closed half space, which is, of course, convex. The same argument works for the superlevel sets, so we're done. All right, for our next example, let's look at what's called the internal rate of return. So this is actually one of my favorite because we see quasi-convexity show up in, otherwise normal settings. So the internal rate of return of a cash flow is given by this expression here. We take the infinium, where r must be positive, where the present value, or PV, must equal to 0. And the PV is given by this expression here. So my claim is that the internal rate of return is quasi-convex in X. And the proof is elegant but straightforward. So if we take the internal rate of return to be greater than or equal to some r value, this is the same as saying that the present value is greater than 0 for all r within a range of 0 to r. So the R superlevel set of IRR is exactly the intersection of open half spaces. Each one is convex, and of course their intersection of convex sets is convex, so that means that every superlevel set is convex. The internal rate of return is quasi-convex. Alright, next let's look at the first order conditions of quasi-convex functions. But first, let's look at the first order conditions of regular convex functions just to remind ourselves. So on the left is the first order condition for a convex function. So what we showed before is that the gradient gives us a global underestimator of the convex function when it's set to 0. Right, because when it's set to 0, this term goes away, and we found the f of y, which is greater than or equal to f of x for some x for all y of the function. On the other hand, the right-hand side shows the first order condition for a quasi-convex function. So you can read this as if y is in a lower sublevel set than x, then the gradient of x must point away from y. So back to our convex function on the left here. So if the gradient of f is 0, that means, like I just mentioned, x is a global minimizer. On the other hand, for the quasi-convex function, the gradient being 0 does not imply x is a global minimizer. So why do we care about this in the ML context? Well, a lot of functions we care about in optimization aren't actually convex, but they're quasi-convex. So this sublevel set, stuff is really what's, doing the work when you want, guarantee that you can solve something, or when you want to compare candidate solutions. So with that said, see you next week.